Good afternoon, everyone. Today we're going to be taking a look at how energy changes shapes, if you will. So the process of converting energy. First of all, I know this does say Unit 3 energy. This is an older presentation, so you can kind of just ignore that for right now. We're not going to worry about that. But the idea of converting between different types of energy is an important aspect of this class. And so I want to go over it a little bit with you right now to make sure that you kind of understand the process and some of the ways that this takes place. So energy conversion is what happens when energy changes from one form to another. So we can sometimes call this conversion, we can sometimes call this transformation, but regardless of what word we choose to use for it, we are talking about energy that is starting as one type of energy and it's becoming another type of energy. So whether that's converted or transformed, whichever kind of word you're choosing to use, it means the same thing. So let's say that you have a match, and on the tip of the match, there's all this little ball of chemicals that you have to strike on the striker. And so that's chemical potential energy. And once you strike that match and it starts to burn, the energy that's coming off of that fire is thermal energy. It's the energy of heat. And so we would say that that's a chemical potential energy being converted into thermal energy. And so that would be the energy conversion in that example. So we're starting with one type of energy and we are ending with another type of energy. Now, this involves work being done. So remember that anytime that we're dealing with energy being transformed or energy changing from one type to another, something has to actually cause that to happen. There has to be work happening here. So if I have 20 joules of energy in one form and I do 20 joules worth of work, I will wind up with 20 joules of energy in another form. It's the same amount of energy kind of as we move from one thing to the next. So kind of always keep in mind that energies will transform back and forth, but we still have to kind of remember what we were doing with work and power describing how quickly energy is transferring from one object to another. So work is still something that we have to be aware of as we're dealing with this scenario. Now, kind of throwing back to something that we talked about with momentum, energy is what we call conserved. That means that we have the same amount of energy at the beginning and at the end. So when energy is transformed from one form to another, it is often the case that some of the energy ends up being in a form that we don't want. But that doesn't mean that we've changed the amount of energy that we have. We will call this what we say wasted energy. It's just energy doing something that we don't necessarily need it to do. It's not the type that we want. So for example, with a light bulb, if you get up close to a light bulb that's been on for a while, you'll notice it's very hot. A lot of energy comes off of light bulbs in the form of heat. That's not the reason that we have light bulbs. Okay, we have light bulbs because we're looking to get light energy out of them. So that would be what we consider wasted energy, but it's still part of the total energy output of the light bulb. And so therefore energy is still being conserved, even if some of the energy that we're getting isn't the type of energy that we want. And so we want to kind of consider that the amount of energy that we have at the beginning of our problem, our initial energy, and our final energy are still going to wind up being the same, even though our final energy, some of that energy is wasted energy, and some of that energy is considered useful energy. So again, with the light bulb example, heat would be a form of wasted energy, and the light would be our form of useful energy. It's the one that we're actually intending to get. So kind of putting that example out there again, with a light bulb, we're going to put electrical energy into the light bulb, and then we get heat and thermal energy, or heat energy and light energy out of it. We're only really interested in the light energy. So thermal energy is considered wasted, but it is part of the total amount of energy that happens. So we're still conserving energy as we go through things. So kind of a slightly more complicated example would be like a rocket. So rockets have chemical energy. We store all this rocket fuel inside of them. That's a form of chemical energy. And we're going to convert that chemical energy into something that's really useful, kinetic energy. We're going to light the rocket fuel and cause it to fly up in the air. but we're going to get some extra wasted energy that's just really not that useful to us. So in this case, it's heat and light and sound. Okay, a rocket could still fly up into the air if you couldn't hear it, or if it wasn't heating up the ground underneath it, or if it wasn't producing light in the middle of the evening. Okay, those are energies that are still there. They're just not useful. So they're kind of, they're wasted. So they're not part of kind of the useful energy that we've got. So sometimes we'll have one type of useful energy and lots of little things that are kind of wasted. But it all makes up the total amount of energy that's happening here. So in order to kind of diagram this out, we'll use what's called a Sankey diagram. Basically, a Sankey diagram has a bunch of these arrows, and the arrows that are things that we're not necessarily using are going to be, they're kind of curving away, if you will. So in this case, we've got a car that's driving. We've got 80 kilojoules of energy from the fuel, kind of in the fuel tank. So there's our chemical potential energy right there. And some of that energy gets converted into heat, which is escaping the engine. So the engine's naturally going to start heating up as it does. And so I'm going to have heat of 50 kilojoules worth of energy. I'll have another source of heat that's going to happen because of internal friction in the engine. This is why oil changes are so important, is that it reduces the total internal energy of the engine. And then finally, I'm going to get some heat that is just used to overcome air resistance, to keep pushing the car forward, if you will. So, and if I add up all of these together, you can see that I started with 80 kilojoules on the left of my diagram. And if I do 50 from this one, plus the 10 from down below, plus the 20, the final 20, that's also going to equal 80. So I have the same amount of energy going in to the engine as I have coming out. It's just only some of it is useful. And this is going to be what we call our principle of the conservation of energy. This is one of the more important principles in physics, and it basically says we can't create or destroy energy, but we do have the ability to change it from one type to another. So to kind of put that in text for you so that you can write it down, conservation of energy means in any energy conversion, energy can be transformed, but the total amount of energy that we have before the conversion and after the conversion is going to be constant. And this will be true unless something is intentionally adding or removing energy from the system. So energy cannot be created or destroyed, but I can change it from one type to another. Just like a light bulb takes electrical energy and turns it into heat and light. So I'm not creating or destroying energy, I'm just changing what that energy looks like. Now, the most common energies that you're going to be working with are potential and kinetic energies. We have lots of different energies, but these are the ones that you'll be seeing probably the most frequently. And also, they're the only ones that you're going to have to do calculations with. So any kind of math-related stuff is going to require understanding potential and kinetic energies. So I've got two equations right here. The first one is gravitational potential energy. So this is that energy of height that you would have seen from doing the vocabulary or any of the previous work. And this I can find by taking the mass of an object. There we go. Mass of an object times the object's gravity times its height. And sometimes I'll just abbreviate this on the board as just m, g, and h. So just to kind of save myself. Early on in the semester, we talked about the acceleration of gravity. The acceleration of gravity on Earth is always going to be 10. So you kind of know this number already going in. So if I was dealing with a 4-kilogram ball and it was 2 meters up in the air, I could take, there's 2 kilograms, here's meters. I do 4 times 10 times 2, and I would wind up getting my total of 80 joules of force, or 800 joules of force. 80 joules of force, there it is. Bloop. Easy. The other equation that you'll wind up doing a lot of work with is kinetic energy. So kinetic energy is the energy of anything that is moving. The equation is a little bit more complicated. Again, you'll see that we have mass present here. So there's my m variable. In this case, because we're talking about an object that's moving, we have to take a look at its velocity. And this velocity is being squared. So we're not just multiplying it like we did with momentum. This time it's squared. So if I had an object that had a velocity of 2, and again, I've got, 4 kilograms worth of mass. If I wanted to figure out the total amount of energy, there's 2 meters per second. If I wanted to figure out the total amount of kinetic energy in that object, I would do 2 squared, which is 4, times 4, which is 16, divided by 2, and I would wind up with 8 joules of energy here. Now, if we are dealing with just gravitational potential energy and kinetic energy, we'll sometimes refer to this as mechanical energy. So this is kind of like the sum, or if I add up both of these things together, we'll call them mechanical energy. As an object is changing height and it's changing speed, so let's say that I have a ball that's falling towards the ground maybe, its total amount of mechanical energy stays the same, even though its gravitational energy might be decreasing as its kinetic energy increases. So that would be an example of a situation where potential energy and kinetic energy might be changing. Can you think of any situations where you might have potential energy and kinetic energy increasing at the same time? So this might be like, we'll go back to that rocket example. All right, a rocket goes up as it's increasing in speed. So its gravitational potential energy is increasing because it's going up into the air, and its speed is increasing, so its kinetic energy is also going up. So like that rocket ship example would be a situation where both of these might increase at the same time. And they're increasing because I'm losing gravitational potential energy, chemical energy. So I wanted to do just a quick kind of math example here just to show you how this works. So a ball is dropped from a height of 15 meters in the air. How fast will the ball hit the ground? So this is a classic conservation of mechanical energy example. And just like every other conservation law, I'm going to start by stating that two things are set equal to each other. So I'm going to say that my energy initially, so this is the starting point, and I'm going to set that equal to my final energy. So I'm not losing energy, I'm not gaining energy. I'm going to have the same amount at the beginning of the problem and at the end of the problem. Now I'm going to define what that type of energy is. So I see that my ball is being dropped from a height of 15 meters in the air. It is in the air, which means that I have gravitational potential energy. So I'm going to start off by saying, hey, this is gravitational potential energy, or GPE. And I'm asking how fast will it hit the ground? Well, if I'm talking about how fast something is going, that's definitely going to be a kinetic energy problem. So once I've identified my different types of energy, I'll go ahead and substitute in those equations from the previous slide. So I know this is going to be mass, I've got gravity, and I've got height, and I'm going to set that equal to 1/2 mass velocity squared. All right, so far so good. I do see that I've got a mass on both sides of my equal sign, which means in this case, mass will actually cancel out. The weight of the ball doesn't matter. It could be very heavy, it could be very light. In the absence of air resistance, all objects fall, or they fall with the same acceleration. So the size of the object actually doesn't matter. So I know that gravity has a value of 10. And I'm starting at a height of 15 meters. And I'm going to set that equal to 1/2 v squared, because I canceled out my m. 10 times 15 is 150. So I've got 150 is equal to 1/2 v squared. I'll multiply both sides of this equation by 2 to get rid of my 1/2. So that'll tell me 300 is equal to v squared. And at this point, it's just calculator time, because I'm going to take the square root of both sides. And I find that the final velocity of the ball, which is what my question is asking, how fast will it hit the ground, is going to be equal to 17.32, and that's in meters per second. So this is an example of how you can solve a conservation of mechanical energy problem in kind of a easy step-by-step fashion, understanding what you have to do. So kind of in summary, we've talked about conservation of energy and conversion, how I can change energy from one type to another, the role of work that we did, and then what it looks like if energy is being conserved and how we can graph that using a Sankey diagram. And then we wrapped up with mechanical energy and a math example for converting.